of IASTA. I think we have a very exciting talk today by Professor TC from National Taiwan University. And TC has been a very good friend of mine from my PhD time, and he was a senior to me. And we have a lot of fun memories in because we both are awarded the same fellowship for PhD program. And it's a very interesting topic. Mostly, a lot of time we ignore about the ultrafine particles when we are still talking about PM 2.5, PM10, but we are ignoring this impact of these ultrafine particles. And today we are going to hear from Professor TC about the impact of these 100 nanometer less than 10 nanometer ultrafine particles on air pollution and the exposure. So I request Professor Ashwin Kumar to introduce Professor TC.
Okay. Thank you, Professor Manoranjan Sahu. So I hope I am audible to everyone.
Yes.
Yes.
So hello, everyone. I am Ashwini Kumar. I am from CSI National Institute of Oceanography. And it is indeed a great pleasure to have Professor Hsio, I hope I pronounced it properly, as today's speaker. Currently, he is a professor in Graduate Institute of Environmental Engineering at National Taiwan University and holds a joint appointment as Associate Research Fellow at the Research Center for Environmental Changes, Academia Sinica. He earned his PhD in Energy, Environmental, and Chemical Engineering from Washington University in St. Louis in 2009, and an MS in Civil and Environmental Engineering from Stanford University. Professor Hsio research focuses on particulate matter measurement and monitoring, nanoparticle generation and ultrafine particulate matter measurement, aerosol and cloud microphysics, and particle instrumentation. So previously, he has also held academic and research position at National Central University, Virginia Commonwealth University, Academia Sinica, and at the US National Institute for Occupational Safety and Health. He is in the editorial board of several well-known journals, including Aerosol Air Quality Research and Journal of Hazardous Materials Letters. So Professor Hsio is a well-known researcher and has received several numerous academic honors, including the Research Achievement Award and Teaching Excellence Award from NTU's College of Engineering 2022, the Distinguished Young Scholar Research Proposal Award from Taiwan's Ministry of Science and Technology in 2018, the Hsio Sen Award from Taiwan Association for Aerosol Research in 2016, and AIHA David L. Swift Memorial Outstanding Aerosol Paper Award in 2012. So his research accomplishment is also reflected from his Google Scholar profile, which I just checked before this presentation, and it indicates a total citation of approximately 3,500 with an H index of 35. So without delaying it further, I invite Professor Hsio to deliver his talk on the title Below the Cutoff, How 10 Nanometer Monitoring Limit Reshapes Ultrafine Particle Source Apportionment and Lung Deposited Surface Area. Professor Hsio, please.
So thanks. Hi everyone. Thanks for a kind introduction, and also I would like to thank the IASTA for the invitation and Professor Sahu for arranging it, and also the kindest introduction by Professor Kumar. So the topic I have picked today is below the cutoff, how the 10 nanometer monitoring limit reshape ultrafine particle source apportionment and long deposition surface area. Because I did recently, I focused on the ultrafine particles research. So that is, I think I can share some of the results with you guys. And also, if you have any question, I feel free to stop me, or we can have a brief discussion afterward. So first, I want to give you an argument in the one sentence before I started, so you know where we are heading. So the lowest oxygen limit we choose for routine ultrafine particle measurement, 10 nanometer, that is currently the criteria, and not criteria, the limit is not a technical for no. It quite decide which source, and we can see at all, and how we estimate the dose that people actually receive. And the talk has to have the first one. I build the case that mass concentration is no longer a sufficient metric. I think probably you already know, but I will repeat again and introduce long deposit surface area at the alternative. That is one I think will probably be a potential very probably be the index we will use later on for ultrafine particles. In the second one, I showed that 2-month campaign in New Taipei City found that when we measure below the 10 nanometer flow, what happened then? So for 30 years, the equality measurement has run one metric, PM2.5 mass concentration. I think we did a lot study on that one. The PM2.5 control has produced a real and important health benefit. I want to be clear about that from the start. You can see, but the benefit is not proportional to the mass removed. The map on the left show population weighted at PM2.5 rising before 2011. The decline occurs many regions afterward. At the same time, happy studies evidence suggests that health effect per unit PM2.5 can be steeper in clear region and near local sources such as traffic. In Europe, the slope is 3.75 deaths per 100,000 per microgram. R square is 0.85. Across a higher concentration Asian region, however, the slope is 0.9. So I should be honest that you can see Asian panel, that one, the R square is 0.28. There is a great deal of the scatter and some of it is certainly confounding health system, age structure, exposure misclassification. I'm not asking you to read the cultural exposure response of the regression. What I'm asking you to notice is the order of the slope, which holds across several independent analyses. One explanation is that equal PM2.5 mass can represent very different particle population. As regional mass falls, the local ultrafine reach source account for the larger share of the biological relevant dose. So PM2.5 remain essential, but it may no longer be sufficient by itself. As we clean up mass, the health effect per unit mass appear to go up, and which tells us mass is no longer telling the whole story. Then what is the alternative, or what can we see, or what is the next? Here is the mechanical reason, and it is really just geometry. I think it's a really simple one. You probably take this through the aerosol class and take a fixed amount of mass and distribute it across three sides. Like here, we just quick do a simple mass at 10 micro. Coarse particles 64 particles at 2.5 micron, or a million ultrafine particles at 0.1 micron, all the same mass. Now look down the table, surface area per particle collapse as you go smaller, but total surface area per mass go up the other way, 1, 4, and 100. For the same microgram sitting on your filter, the ultrafine fraction present roughly 100 times the surface. So this particle also penetrate efficiently into the respiratory system and can carry organic compound and metals on their surface. So mass measurement can be low while particle number, reactive surface area, and deposit dose all remain high. That is the fraction we risk missing. So mass count the wrong thing. For ultrafine, the dose that matters in number and surface area, and the mass is nearly blind to both. So the systematic effect we attribute to PM10 or PM2.5 often come from the ultrafine fraction hiding inside that mass. So ultrafine particles are conventionally defined as particles smaller than 100 nanometer. This is a size definition under not a single chemical class. So their property depends strongly on the source and atmospheric processing. They can emit directly from high temperature or combustion process, form immediately after exhaust plume cools, or produce in atmosphere through gas to particle conversion or the new particle formation process. The compound may include sulfuric acid, highly oxidized organic material, black carbon, metal, and many other species. Physically, ultrafine particles have a weak inertia, strong Brownian motion, high specific surface area, and rapid calculation. Their number concentration can change within minutes to hours near a source. Some freshly formed particles disappear quickly by dilution, evaporation, coagulation, or surface deposition, while others grow into larger modes and are transported further. These dynamics are why ultrafine particle monitoring requires both high time resolution and source relevant locations. And almost every distinct property of ultrafine particle follow from the one thing, the surface to area ratio. High curvature drive the volatility behavior, larger surface area drive the reactivity, strong diffusion drive the deposition. So regulation is beginning to recognize the limitation, the mass. So although the approach are still uneven, the WHO lowered its annual PM2.5 guideline to 5 microgram per cubic meter in 2021, and for the first time include so-called group practice statement for ultrafine particle number monitoring. The United States strengthened its primary annual PM2.5 standard to 9 microgram per cubic meter, in 2024. Europe has moved further to a routine ultrafine particle monitoring. Now, I think they require the routine ultrafine particle monitoring before the end of this year. Directive 2024-288-1 require ultrafine particle measurement at urban monitoring supersite and at location where high concentration are expected. What are those places? For example, roads, airport, and ports, industrial area, and location affected by domestic heating. One statement of this slide needs to be interpreted carefully. The suggestion that meeting the 5 microgram PM2.5 guideline will probably keep ultrafine particle population within a acceptable range come from later scientific perspective, but not from WHO guideline itself. It is a useful hypothesis for some regional background, but should not be treated as universal. What does that mean? Here I show you like a recommendation for maximum 5 microgram will likely keep ultrafine particles air pollution within acceptable. That is, assume they are proportional to each other under the 5 microgram limitation. Our roadside data provide a direct test of whether low particle mass necessarily means low particle number. Later on, you will see the result. Of course, if that is not the case, you will see later. Traditional air quality standard focus on the mass concentration of PM2.5 or PM10 may not adequately represent true environmental impact and health risk, especially when aerosol is dominated by ultrafine particles. I want to spend 2 slides on the source that make the cutoff problem concrete, that is aviation. Aviation fuel is mainly medium to long-term hydrocarbon, relatively low in volatility and stable in composition. In turbine, combustion is continuous diffusion combustion at high temperature and high pressure. With a very high air-to-fuel ratio and a design that promotes strong air flow mixing, overall combustion efficiency is extremely high. So every combustion process generates black carbon, but there is enough oxygen inside the turbine to oxidize most of what initially formed, so only trace amount appear in high temperature primary emissions. And gasoline, especially diesel engine, are on the opposite. So intermediate cycle create localized fuel-rich zone. Combustion is incomplete, and direct carbon, black carbon emission are much higher. So what matters more in aircraft emission is the gases precursor. Once the hot exhaust leave the engine, it enters a cool secondary formation stage. The exhaust mix with ambient air and cool. Volatile and semi-volatile species that were originally in the gas phase include the lubrication oil, nuclei, and condense. They generate large amount of new ultrafine particles, mostly volatile in composition, even smaller in diameter and vast in number. So the two formation mechanisms are fundamentally different. A row vehicle mostly emit particles. Aircraft largely emit gases that become particles in the atmosphere a short distance downwind. So if you only measure non-volatile particle number, which is what the engine certified framework does, aviation real particle burden is invisible. But nowadays, people start to recognize actually aircraft emission is a very important source for the ambient ultrafine particles. The environmental and health impact of aviation emissions may well be underestimated, particularly around airport, and that they probably also part of the particle contribute to less than 10 nanometer regime. So the table summarizes the typical contrast report in many near-source studies. Aircraft plumes are often characterized by strong nucleation mode around 10 to 20 nanometer, but I think also the particle less than 10 because the formation mechanism and comparatively low black carbon to number ratio, that is a signature. Road traffic commonly produce a broader mode from a few tens to roughly 100 nanometers, often with more black carbon. That is the kind of the tracer and sometimes a signature we use to pin out or to look the traffic emissions. The spatial behavior also different. Railway gradients are usually steep, close to road, while aircraft plume can remain very high. Not really verified, but it can last for several kilometers downwind until favorable condition to disperse it. However, the emission factor range span orders of magnitude. The value on this slide should therefore be used as a source fingerprint, not a universal claim that aircraft always emit a fixed multiple of the road traffic particles. This example explains why the network that measure only total mass or only particle above fixed lower size can miss source that is present in the air. So why this become an international priority now? So international attention has increased for two related reasons. First, epi and toxicological study report short-term and long-term association involved respiratory, cardiovascular, systemic, neurological, and genotoxic outcome. Some associate persist after adjust for PM2.5, although the evidence is not yet uniform enough to support universal numerical ambient ultrafine particle standard. So far, we don't have that. But second, the measurement science is now mature enough to support coordinate exposure modeling. We now can harmonize particle number method, establish urban and background network, identify hotspot, and build a long-term database need for stronger epidemiology. This is the logic behind the WHO group practice advice and the expansion of networks such as ATRIS in Europe and ASEAN in the United States. Monitoring does not have to wait until every pathway and regulatory threshold is fully settled. Standardized monitoring is what allows those questions to be answered. I think we are here to do that. So we are in a window where the monitoring decisions are being made before the epidemiology is settled. So which means size range we choose now determine what the epi will be able to find later. So if the network starts at a 10 nanometer, then the exposure metric in every study built on them start at the 10 nanometers too. So why might ultrafine particle be biological important? Two dimensions work together. So physics and chemistry, I mean also physics and also chemistry. So on the physics side, the deposition curve show that Brownian diffusion becomes increasingly important as particle size decrease. Ultrafine particles can therefore deposit efficiently in the head airway, truncobrachial region, and the pulmonary region, depends on their exact size. So they also provide high surface area per unit mass. We say that before, but here again, we noted actually the really small particle actually deposit very efficient in the head region, not just only pulmonary region. So on the chemistry side, particle surface can carry reactive organic compound and metals. This compound may promote reactive oxygen species, oxidative stress, inflammation, and downstream cardiovascular and respiratory response. That is why recently oxidative potential catch people's attention and can be used as an index to study the health effect of this PM or the ultrafine particle. The conclusion is not that every ultrafine particle has the same toxicity. Toxicity depends on size, deposit dose, surface property, composition, solubility, and the biological susceptibility. Size alone is not toxicity, but size strongly controls how the chemical exposure is delivered. So two conceptual hypotheses, we go further a little bit, are useful for organize this mechanism. The ultrafine particle hypothesis emphasizes efficiency deposit. High specific area, we already said that again. And it is particularly relevant to poorly soluble particles or which particle surface itself. Later, I will have a cartoon will show that also can deliver biological response. The Trojan horse hypothesis as the role of the particles as a carrier. So metals, pH, and other compound can present within or on the particle, enter cell or organelle, and then be released in the intracellular environment. In some cases, combined response can be non-additive, can be amplified, the synergetic effect. These are mechanics framework not proof that every ultrafine particle follows the same pathway. Also, only a fraction of the inhaled ultrafine particles is expected to translocate from the respiratory tract into like circulation or other organ. The value of this hypothesis is that they connect particle size, surface composition, and solubility in testable way. So here, I want to say between the two hypotheses, the metric that matters is surface area, either as a reactive interface or as the carry capacity. Neither is a mass hypothesis can do. And a particle size division that separate number surface area here is what I'm saying, the cartoon in the middle row. And the volume or mass, those metrics emphasize different parts of the same aerosol. Number concentration is the most sensitive to newly formed or ultrafine particles. Surface area shift toward somewhat larger ultrafine soot or lower accumulation particles. Volume and mass are dominated by the accumulation and coarse modes. This is why the rush hour and midday feature are obvious in the numbers division, but can be weak or absent cannot be seen by the mass concentration. The source ring on the right. You can take the yellow and the blue one. Make the same point. In the example shown here, traffic-related particles account for only about 20 to 30% of the PM2.5 volume, while traffic and photochemical age particles account for more than 95% of ultrafine particle number. The precise percent are study specific, but the metric dependence is general. Number, surface area, and the mass are therefore not interchangeable. They answer different questions about the source activity, particle tissue contact, soluble material, and regional aerosol. A full size division preserves this distinction. So that is size division review what mass concentration structurally cannot. New particle formation, traffic peak, optical property, and health risk. So there is one more layer of the physics that matter for long deposit surface area. particle morphology. I think that is also a quite interesting topic. And SMPS classifies particle by electric mobility. It does not directly measure geometric shape, material volume, aerodynamic diameter, or acceptable surface area. For a compact sphere, the size coordinate are closely coordinates are closely related. For a channel like a set aggregate, the same mobility diameter can correspond to very different effective density and real surface area. We test the diffusion. I do not really provide the result here. I just briefly describe. We test the diffusion control branch using silver nanoparticles. We generate channel-like aggregates. Similarly, center part of the aerosol into compact particles. Select both morphology that mobility diameter from 20 to 60 nanometers and measure chamber wall loss decay. When plot against mobility diameter, the two morphology follow the same diffusion control trend reasonably well. And the period difference were approximately 3 to 16% difference, within the largest difference at the 30 nanometers. So what does that mean? It supports mobility diameter as a nature coordinate for Brownian diffusion. It does not mean that aggregates are equivalent to sphere for surface area, charging, aerosol behavior, interception, or impaction. So what is I plug one cartoon here. So there is a set of points. On the left side is the diffusion control. So on the left hand side, the electrical mobility still work quite well. But on the right hand side, if the aerodynamic behavior control, you have to use the other diameter, effective density taking place and become an important role. Then you have to get involved in those like initial effect. So when LDSA is calculated for soot-rich aerosols, morphology and effective density remain important uncertainties. For diffusion, mobility diameter is enough. Beyond the settle, as I say, you also need density or morphology information. Otherwise, the surface area those come out systematically too high. So long deposition surface area, or LDSA, is the surface area of the inhaled particles estimated to deposit in a select reservoir region. And the size distribution approach is shown on the left. That is based on some assumption at each size we have to first multiply the number constitution by assumed particle surface area and by size-dependent deposition efficiency, and then integrate over the distribution. This approach provides a size result information and can estimate deposition separately in the head, truncabrachial, or pulmonary region. It also requires assumption, like I say, about particle shape, density, hygroscopic growth, and the breathing condition. I think the last study is about the effect of the hygroscopic growth, and it should be taken into consider when you really want to estimate the long deposit real one in your reservoir system. The second approach is diffusion charging. That is a more experimental way to really determine the LDSA. As the nanoparticle surface area monitoring, these instruments are fast and practical. But anyway, skip that one. The response is best constrained over roughly 20 to 400 nanometer. However, the response is calibrate dependent and can change with size diffusion, morphology, density, and charging behavior. For consistency with the source result model on the next slide, we are going to talk about the LDSA ratio should be defined. Defined here is LDSA measured by the Ansen. Ansen is one instrument used. That is the equation I show in the middle of this slide. Calculate from the particle size division. That is another one more based on the spherical assumption. This ratio can tell us something. The morphology is considered one of kind of index to reveal the morphology. So the key is LDSA is the right kind of metric. It tracks the particle cell interface, but the way we routinely measure it starting from actually 20 nanometers. Everything below it, we are extrapolating. Actually, we cannot see the contribution from really small particles, at least for this instrument. But you still can do, through the integration, you still can use, I mean, particle if you measure particle less than 20 nanometers. So published urban LDSA value very widely. The table range from few tens of the square micrometers per cubic centimeters in several European cities to more than 300 in Delhi during the report campaign. These numbers should not be treated as a simple ranking of the city. They were obtained within different instrument size range, deposition convention, averaging period, seasons, distance from source. Even within one city, moving from urban background location to roadside or hotspot can change LDSA substantially. That is also the challenge for like a study or investigating the ultrafine particles. The important message is that LDSA is strongly microenvironment and source dependent. And citywide PM2.5, normally you cannot see that kind of dramatic change within a short distance. So this location dependence led us to combine LDSA with source apportion in our earlier work in Taiwan. Here, that is one of the publication I really like to share with you. This early study was conducted in a motorcycle dominate urban environment. I believe in India, probably a motorcycle is very important transportation mode, and I think for Western country, they cannot imagine how important and the source, emission source it is, and how strong or how significantly can affect our air pollution. And we combine the PM1 source apportionment with a particle size division and direct LDSA measurement. A key result was the motorcycle flux track the variation in LDSA more strongly than it tracked equivalent black carbon. This is consistent with the motorcycle fluid that emitted high particle number concentration and surface area without equally strong black carbon signal. The interpretation should be therefore be expressed as a difference in black carbon to number or black carbon to LDSA relationship compared to the Western countries the result, because rather than simply saying that motorcycle emit no black carbons, it just the efficiency, the engine efficiency is totally different. So this result illustrates why one source marker cannot represent all traffic exposure. And PM1 emphasizes a larger mass dominant source. Black carbon emphasizes that LDSA remain sensitive to the surface area of the traffic-related particle population. And in a two-wheeler city, black carbon is not really a good traffic. It is, of course, it is the traffic tracer. And the mass is the wrong exposure matrix, actually. LDSA and the particle numbers see the fleet that is actually on the road. If your city run on the 2 or 3 wheelers, the result is probably more transferable to you than any measure in Europe or US. And we then use a multiple linear regression framework to connect source result size division with the LDSA monitor. At each hour, the major NSEN signal was represented as a sum of the PSD-derived LDSA from each PMF factor multiplied by fit source specific coefficient. Why is that? The coefficient alpha, we call it alpha here, is operationally the ratio of DSA measured by the NSEN to the LDSA calculated from the source result size division. And why is that? Because using PMF first, we can try to get this alpha for different kind of the factors. I mean, the PMF factor, the sources. The different alpha value indicate that the same field-based PSD calculation does not reproduce the electric response equally for all sources. So he revealed the morphology effect for different sources. Morphology is the one possible reason, especially for stud aggregate. However, alpha can also reflect difference in size distribution, accessible surface area, effective density, charging response, hygroscopicity, and instrument calibration, but hygroscopicity normally is neglected in this case. I therefore use it as a source-dependent response factor, not a unique measurement of the fractal dimension, but still tell us some information about the fractal. The broader lesson is even the health relevant metrics such as LDSA depends on how the aerosol is measured and represented. So the key is ratio between the two LDSA methods. One is measured, the other based on the charging. The other is estimated theoretically based on a PSD. Treat as a calibration problem to minimize. It is actually a morphology signal, so it should not be minimized. So if you operate an SMPS and the electric LDSA sensors side by side, you are already measuring more than you think you are. You can see the morphology effect based on this ratio. So let's go to the main point here now. So with the background in place, I now come to the central question of this lecture. So what do we lose when routine ultrafine particle monitor begin at 10 nanometers? We examine three consequences. First, whether the lower cutoff change the observed diurnal pattern. Second, whether it changes the source resolved by PMF. Third, whether it changed the region and matrix of respiratory deposition. So the metric connect the side distribution to health throughout the section is deposit of particle number and long deposit surface area. That is what I mean. So here, back to the record, some published regulatory gap. So WHO 2021, that is a left column, non-binding guidance, particle number lower than 10 nanometers, no urban minute. Monitoring merely recommended, no size requirement, no measurement standard. EU Directive 2024, we mentioned previously, right column, legally binding. Ultrafine particle are defined as below 100 nanometer, measured as particle number, with the same lower limit of the 10 nanometer, but before actually is 7, but later on they moved to 10. Mandatory for all member states, supersize at 1 per 10 million urban population hotspot, as we mentioned, airport. And formal CEN standard, as I say, that one that is lower limit is 7 nanometers. And this enforced since December 2024, full application by December this year. And that is a serious framework. And I want to be clear, I support it, actually. I really, not just only because I do the ultrafine particle study. Mandatory number and size distribution monitoring is a major advance over mass alone. But read a sentence at the bottom. Ultrafine particle technically means below 100 nanometers, and standard capture everything above 10 nanometers because particle above 100 nanometer are only 10 to 30% of the numbers, which means 7 to 90% sitting below 100 nanometers. So particle number gets used as a surrogate for ultrafine, that is a fair guess. And the definition says below underneath, like I say, and both framework draw their floor exact the same place, and the floor is what I want to examine. So 10 nanometer, and the two European methods met the boundary just apparent. The two one is EN 16976. For particle number, a full flow Built-on-based condensation particle counter in counting mode. The 50% detection efficiency right at the 10 nanometer up to roughly 3 to 5 micron, and got to have a 1 minute resolution. And standard 17434 for the side diffusion, a mobility side diffusion, DMA bipolar diffusion charging, CPC, from 10 to 800 nanometers. And resolution is 2 to 10. minute. Both are regulars. Both begin as a 10 nanometer, not because, again, where the particles stop, but because below 10 measurement get harder and noisier and more expensive. So it's words to begin specific about why, because I don't want this to be sounds like an easy question. Below 10 nanometers, three things go wrong at once. The CPC counting efficiency fall off steeply and becomes strongly depends on the working fluid. Diffusion loss in the sampling line become large and correction sensitive. And the bipolar charging efficiency dropped to few percent. So inversion became amplified noise rather than signal. So going lower means a particle size magnifier, that means even below 3, or the other dimensional glyco CBC carefully lose characterization and a great deal more operator attention. For a network of the dozen of the size running continuously for years, that is a legitimate engineering constraint. So that is a feasible issue. The gap is not oversight. It is deliberate and defensible practical flaw. But my question is simple. What does the flaw cost us? So that is what we want to answer. So this is the field, the field result. The time series on the left show that particle number repeatedly increased during the daytime, together with solar radiation and the change in boundary layer. The warm color on the right-hand side, the scalar part, identify late morning and the middle day observation. The x-axis is pin1. The co-locate continuous mass processing, not the pin 2.5, sorry. And the correlation between pin1 and ultrafine particle was weak, with a report correlation coefficient about like 0.21. Many observations with moderate pin1 still had a high ultrafine particle number concentration. The dashed line here represent the WHO high particle number concentration reference, that is 20,000 particle per cubic centimeter for 1 hour mean. Because our native data have finite time resolution, this line should be used as a screening reference unless the observations are average on matching the 1 hour basis. It is also better described as a high PNC benchmark, not a health risk threshold. The conclusion is never is clear. At this site, particle mass was weak surrogate for short-term ultrafine particle exposure pattern. Low mass did not guarantee low particle number. So that is a clear message I want to deliver first. So now to the heart of it, what actually changed when you move the floor? We try to measure the particle down to like 3 nanometer. That is the nano DMA can do. Not you don't need a PSM. We ran past the PMF twice on the same campaign, same site, same period, and same pre-processing. The only difference is the lower bound. So one is down to like 3 nanometer, the other is down to 10 nanometer. On the left-hand side, conventional range, that is 10 to 1,000 nanometers, which is exactly what EU directive would give you. It resolved three factors cleanly. That is fresh traffic, age traffic, and background. Nothing about that solution looks wrong. So if someone hand it to you, you probably publish it. On the right-hand side, you extend the lower bound to about 3 nanometers. And now you see the fourth factor appears, the fourth one, photochemical nucleation. And it is not marginal, actually. It correlates with the total particle number concentration at R squared, about 0.72. Here, I did not really directly show you the figure, but I reported data. The fourth fingerprint are distinct and diagnosed. The photochemical is bimodal. Nucleation peak between 4 to 10 And the second mode is around 70 to 80, where those fresh particles have grown. Fresh traffic is unimode, around 20 nanometer, correlate with NO at R. Sorry, I do not show directly, but I just describe it. And the peak is in the morning rush. Edge traffic span like 20 to 100 nanometer and correlate with NO2 and black carbon at a point 0.57 and 0.67. Background is the accumulation mode 100 to like 150 nanometer regional transport. That is what we suspect. So here I think most important things is the top right panel is the textbook event. That is it's not the one. It's not really a textbook event. Sorry, that is what we measure, but not in the same campaign. The banana shape, that is what we say textbook like the geometric mean diameter grow from 24 to 58, about 34 nanometer of the growth in 4 hours, and underneath it is chemistry sulfuric acid. That is what can be done. I mean, in the atmospheric probably the mechanism is on the right. So VOC and SO2 oxidized by radical OH or even the ozone to low volatile vapor, which either nuclei brand new particle or condense onto existing one. And there is a subtle damage when you cannot measure below 10. The photochemical signal does not disappear. It gets misattributed to the factor you can see here. In our data, actually 20% of it leak to the fresh traffic, 61% into the age traffic, and 16% to background. So that is a net result that age traffic is overestimated by roughly 70% and the background by roughly 20. So that is the cost. Cutting off the 10 nanometer does not merely hide a source. It corrupts your estimate of the source you did resolve. And correct regulation control only non-volatile particle emission, but studies show semi-volatile particles are more relevant to ambient air quality than previous thought, actually. So the next one is it is not only the source, it changed where the particle, the body of the dose landed. We took the major side division into, we use the MPPT model. You also can use the ICRP model. So the full airway, but this one can give you more parameter you can choose. For example, like here, we can choose the different ages. So for airway geometry, diffusion, impaction, and settling for 4 ages, here 3, 9, 14, 21 years. And here I just pick one example. Look at the pie on the right. The center ring is the share of the total deposit dose by mode. Nanonucleation that is below 10 nanometers, which cannot be seen if you just measure a particle larger than 10 nanometers. That is 30%. Nucleation is 10 to 25 nanometer is 63%. Econ that is 25 to 100 nanometer is 44%. Accumulation is 6%. Now on the outer pie, which break each mode down by region, and watch the pattern is different. The nanonucleation mode below 10 nanometer deposit 43%. I mean, we think this size 43% in the head and 53% in the truncal region. I don't know whether it's surprising you or not, but actually a lot, you can say like 40% actually deposit in the head and only 4% in the pulmonary region. That is the upper airway particles, and so not always the smaller particle get deeper in your respiratory system. So the head is where the olfactory route sit, the pathway linked to the neuroinflammation, that a neurodegenerative outcome. That is also the reason why the European researchers really focus on the ultrafine particles and move out the econ 25 to 100 nanometers, the traffic derived range, and that inverted like 41% in plurality. So that is the alveolar cardiovascular pathway. So the sub-10 particles you exclude are not just only more particles, they deposit somewhere different with a different health implication. And then age. Sorry, I did not, so I skipped that one. But actually, we evaluate the deposition under different ages. So include these small particles, I mean smallest particles less than 10 nanometers, the dominant deposition side shift. Number, surface area, and the mass each peak in different region of the respiratory tract, and a single average mass concentration cannot represent that definitely. So the last slide conclude my talk. So I close with 4 points. First, a sub-10 nanometers particle were not a minor tail. They contribute about like 54% of the total particle number. Second, including them change the daily pattern and reveal the independent photochemical factor. Third, their deposition is regional specific and change the dose ranking by source, by matrix, and by age. Sorry, I did not really show a slide by age. Then the fourth, mass-only monitoring cannot capture this dynamic definitely. So our recommendation is not to abandon PM2.5. It is complement mass with particle number, particle size division, and deposition surface area. And reason we pick the deposition surface area just because it's easy to measure it and is more cost-effective way because the particle size division is too costly. And 10 nanometers should be the minimal operational lower bound, not the final target. Where the technical feasible, if that feasible, network should be extended at least to 3 nanometers. So the broader message is simple. The lower cutoff determines the source we see and the health risk we infer. And thanks for the invitation. And the last slide, just I want to spend a very short time, I mean, try to give you new news. The Journal of the Hazardous Material now spin off the new journal called the JHM Air and open for submission. And there is no article processing charge for anything submitted before June 2028. And here is a QR code. So if you consider, then, but frankly speaking, in the next 2 years, we don't have an impact factor, but we welcome more like nice or good aerosol researchers to contribute and involve in this field. And thank for the invitation, thank for listening. More than welcome to any question.
Dr. Rastogi, you will take forward.
Okay, fine.
Yeah.
Okay, so Professor Sao, first of all, thank you so much for such an interesting and informative talk. It was very nice. And I'm sure there will be multiple questions. So now I would request audience to please raise their hand and we can take the question one by one. In case if you can't speak, you can write the question in the chat box and I will read out for you. And until people start asking question, let me start. So can I ask? So in your just previous slide, Dr. Sao, in your recommendation, you have not included the chemical composition.
Sorry.
So in your recommendation, last point,
Yeah.
you have not included the chemical composition of those particles. So don't you expect if you are talking about the health effect, if you know the composition as well, then it will be more interesting. What do you think?
Yeah, of course. If you can have the chemical composition, that is a plus, not just a plus. It's very. I think everybody agree with that. But the problem still is very costly. Because if you want to know the composition, and one more thing is if you know the size resolve composition, that's even better, right? So you know what is the composition you deliver to which region. That is even better, but the problem just too costly. So that is also the reason why recently people promote the oxidative potential, because if you want to like have the health risk index, why not just jump to some index can directly give you that, not go through the chemical composition. Because
Yeah.
even the chemical composition, there is some um synergic effect. So that is, of course, if you do, or me too, we do like a chemical analysis and try to use that to estimate the health effect or risk. But I think for regulation purpose, maybe not really feasible. That is my point. Yeah.
So when you say it is oxidative, means if we also include oxidative potential, which is certainly better than chemical composition, at least as far as health is concerned, because we know that ultimately how it is going to affect. But at the same time, we also know that at present the assays which are available for the oxidative potential, there are multiple assays, and different assays are more responsive to different chemical species. So that means if you are considering oxidative potential, depending upon what assay you are taking, it will decide whether the composition of the particle is actually meaningful or not.
Yeah,
Yeah.
I do agree. I do agree. Yeah.
Okay.
And
Okay. Just a few query means I will not call it as a question. I will just it is a query for your from some of your slides. So when you are talking about this LDSA, and
uh-huh.
then you show the surface area per unit volume. So in actual sense, when people we are inhaling those particles, so there is a finite possibility that there can be hygroscopic growth within that tract,
Mm-hmm.
and then it will change the surface area. Means actual deposition may be slightly different than what is estimated uh, the way you are showing. So how we
Yeah.
can handle that?
You it's a very difficult question actually. If you really want to study, I mean study means investigate, uh investigate the true like surface area. But I think if you like back to the previous question about the chemical composition, so one thing is based on the chemical composition, you can try to estimate like a kappa first. That is the easy one. Then based on the kappa, you can incorporate this hygroscopicity in your model to estimate the particle growth. And after that, you only can assume the surface, I mean, spheral particles, then estimate some their LDSA. That is doable. I think in some paper and even ourselves, my student, when we know the chemical composition, or if I measure like CCN data to calculate the kappa, I we always use this kind of framework to estimate the hygroscopic effect on LDSA, or estimate the surface area after the hygroscopic growth. But again, we have to assume they are like on the surface and the material, then they grow up without any other like interference, means like organic get involved to change the hygroscopic behavior, those things. So that is what we did. And for your reference, that is, yeah.
Okay, thank you. Just last query. Means you are showing that uh, you can differentiate between photochemical, fresh traffic, age traffic, and then background based on the particle number and size. Means, one of your last slides you were showing that you are categorizing in different uh, categories like photochemical, fresh traffic, age traffic, and background. These four categories you differentiated the particles. Yes, yes. This is the slide. Yeah.
Yeah. So
So yeah,
your
yeah.
question
So
is how
yeah,
or how do
no,
we determine the factor?
yeah. Means my question is, say for example, when you say photochemical, so it is showing at two places. So less than 10 nanometer, new particle are forming. Okay, it can be photochemical if it is depending upon what time it is forming. But when it is around this yeah, 50 nanometer, then how do you know it is photochemical or it is aged or fresh traffic? Means how do you differentiate without knowing the composition? How based on number only you can say that it is whether it is fresh traffic or photochemical or aged traffic?
Frankly speaking, we cannot really know that is true photochemical or fresh particle. Actually, we cannot. We only can provide some supporting evidence. That is always we did for PMF factors determination. For example, like we will do some like a correlation with the other proxy, the gases species, and also study their diurnal patterns, and also the solar radiation correlation, etc. So to figure out which one have evidence, then we name it as list. So of course, there's still some possibility, like you say, the photochemical factor could mix with the other, but it also have the possibility, like the larger size mode, the photochemical is not newly generated, that actually they are due to photochemical reaction and then condense or grows on the particle, existing particle, so they have a two size. And if we have some other chemical composition, we can put those as a PMF, then probably you can resolve or you can make this, I mean, the factor more even clear that probable. And so I also support your point is like a chemical composition is quite important if we could have, but to have the particle size composition down to 10
Yeah,
nanometer
yeah, I
is very
understand.
challenging.
Right.
Yeah, it's very
I agree.
challenging.
Yeah.
Yeah.
Okay, so let us move forward. And I see the raised hand by Professor Sahu. Professor Sahu, please.
Okay. So, TC, thank you so much. A very wonderful presentation on ultrafine particles. But I have a certain, just a query, just to get your insights on it. To make going down to 3 nanometer, you know that you need either nano DMA and things like that.
Mm-hmm.
These are very expensive instrument, right? It will
Yes.
not be accessible to normal researcher or many researchers in India as well as in Asian countries. Very expensive items. So, what are the ways you can suggest? What are the alternative ways? Do you have some insights, ideas how to handle this?
You mean have a cheaper solution?
Yeah, I know. Is
Yes.
there any alternative way? We do not
Mhm.
have an nano DMA. So either kind of modeling approach, for example, I think in one of my work in Washington University, what I had done is I know what is the mean particle size coming from combustion, and I know the what is the kind of what is that spread. I put it as a normal distribution, log normal distribution, and then try to form this size distribution, right? And then try to find out the deposition of the particle, things like this. I'm trying to understand how we can do this type of research when we have a constraint. I think there is a very similar question by one of the attendees. So, what is the way forward to do this when we do not have a
Um,
like this?
I don't have a good answer. I try to answer your question, but I don't know that it is good or not, good enough or not. Come to my mind first, like if you know how to, if you have the CBC,
Mm-hmm.
composition particle counter,
Mm-hmm.
if you know how to tune the particle condensation counter, the condensation particle counter, then you can change the detection limit. Okay. So you don't need have a but the resolution is not that fine, okay, but it's still doable. You only need is CPC. Then you have to change the operation parameters to have a different detection limit. Then you can still have like a 3 or 10, like these two different concentrations, and the difference, but it's still challenging. Yeah, you have to know how to adjust. That is one thing. The other thing is LDSA. I think LDSA sensor is much cheaper than the SMPS. That is also the reason why I believe in European they will pick the LDSA later on as an index because it's more cost-effective way. SMPS for them is still you cannot have them for everywhere. You might have some in certain like monitoring site. Yeah. So that is the two solution come to my mind.
Okay.
And yeah.
So this LDSA is measured by that NSAM nanoparticle surface area monitor you said, right?
Yeah.
Okay.
Yeah.
A little bit less expensive, right?
Yes.
That. Okay.
And nowadays there are different company make a very similar sensors, not just only NSAM.
Okay.
You can have a few brand. Yeah.
Okay.
Okay, Professor Sao, we have some more questions in chat box. If you have time, can I read them out for you?
Yes. The first question is, do you suggest that constant discussion on PM2.5 and PM10 as dominate in air quality research need a replacement or context-specific modification? If I understand the question right, yes, I think that need a replacement. I think I do not think PM2.5 or the mass function is no longer important. Okay, I think the problem so far, what we see is when the concentration get lower and lower, if your concentration is high, then PMS concentration probably is a good indicator. Okay, and that can give you some health gain. But when your concentration down to like a 10 microgram per cubic meter, like within starting to reaching that range or 15 microgram per cubic meter, you will lose your gain through the mass concentration. Then that is also reason why the European country start to search for new index and more closely or directly linked to the health outcome. And I think LDSA or OP are the two potential index they try to have later on, and it's ongoing, and that is complement to the PMS concentration, not replace that one. And the one more thing I can add is the LDSA is more like a physics way. Like I say, you have to have a two dimension, and LDSA is more like the cost-effective solution for represent the physics perspective, and OP is more like another index to represent the else of chemistry or a more cost-effective way to represent that. So you need both, not just only a single one. And yeah, that is my point of view. And currently we write one like a perspective paper to talk about that one. We'll submit to journal soon. And the next question, the relationship between the particle size and their mass contribution. The figure of Daly was glaring. That is what we found. I think probably is this slide. That is the paper research and try to
Yeah. Yeah,
put
it was a
together.
comment actually, not a question, it was a comment. Yeah.
Yeah, and I believe it will getting lower and lower in the near future. Just we have to take a close look, and keep tracking, and also make record. And otherwise, we don't know what's going on later on because you lose the information before. You only know later, and that is I can respond. And while we have instrument restriction to not measure PS less than 200, in such case, use a multimodal log normal distribution approach provide theoretical trend of the PSD beyond. Can you consider those projections provided by multimodal log normal distribution? Is it scientific correct approach? If I understand the question right, the you depends on the constraint first. If you want to have a multiple approach, like to infer the size distribution, it depends on how many point the measurement you have. Like for the Gaussian, if you assume the log normal, you have to have like a 3 point, right? Because you have to constrain your like a total number concentration or geometric mean, geometric standard deviation like this. At least you have to have a 3 measurement in order to constrain. So if you want to have a multimodal and you assume log normal, then you have to have a null like constraint in order to retrieve your distribution. And those also will limit your resolution. How to set this strategy measurement, how far between will limit your resolution. That is what I can think right now. If you can measure those under different point, let's say that. And any question, but I won't answer. Why can lower mass still produce substantial health effect? Why is that? I think the mass still provide, like I say, some meaningful information but anyway, that is, let's say that, just combine, the other's answers. Actually, what can impact your or cause the health risk is what you inhale. The problem is always what you inhale or where they deposit. So definitely the mass concentration is the integral value. It reveals the total amount, but you don't know what and you don't know where. So still, the data will very scattering. Scattering means if you inhale the same amount in Japan or the same amount in China and in the same exposure dosage in Taiwan, definitely the outcome will totally different, even the same person, because the size, the composition are totally different, right? So, but if you lower any of them, of course, you get some gain on it, but the gain will be quite different. So still, there is a high concentration if your mass concentration is quite high, like I say, still you will get a good substantial health like improvement. But when you get down to like lower and lower, then starting you don't see that effect. Then you have to figure out what is the most critical part. And CBC alone can go down 3 sides, but it will give a single number and not the side division. Yes. Yeah, like I say, yeah. So if you have your multiple CPC, or if you know how to tune your CPC, then you probably can have a different size, the concentration. But the problem is their performance is not that stable. That stable is not easy. Okay, it's doable. So it can go down to the 3. That's true. But yeah. If you try to, or if you want to say is, we can definitely just directly that the size cut of the CPC down to 3, then measure the total number concentration. I also agree with that strategy. That is another way that you probably can use to measure the particle total number concentration, but you lost some information about the size distribution. And why can ultrafine particle cause significant health effect of error through they contribute very sorry
Very
little
little.
to
He wanted to write little. So this is
yeah,
yeah.
very little to total. One can cause significant health effect or even through they can they contribute very little to total beam mass concentration.
He's asking that even though the ultrafine particle contribute in terms of mass very less, but they contribute significantly to the health. Why is it so? That is what he's probably trying to ask, if I understood correctly.
Again, the problem
I think
is more
you
like
have yeah
yeah. I
yeah
think we have a very similar question together. So I again, but I interpret this question in the other way. Okay, like some people will ask the question like the ultrafine particle already included in PM2.5. So why can we see those effects when we like do see the PM2.5? The answer is yes, you do. The what we try to say is when you lower the mass concentration, which part you actually lower the mass concentration. Normally that is larger particle because larger particle contribute most of the mass actually. So those particles do not really contribute the health risk. However, you just remove them, you can significantly see the mass concentration go down, right? But you do not see the comparable like a risk, the health risk reduce comparable. And initially you will see some, but later on this effect gone. So the ultrafine particles become more and more important, and also it dominates. So it's still there. It's still there. You don't. So that is the storyline normally we see. Yeah. So I think that is my answer quickly or briefly. So yeah,
okay
thanks.
okay. So Professor House, thank you so much for giving us time for the question answer as well. So now it is the last part of the talk, which is the vote of thanks. I request my colleague Dr. Manish Joshi to give the vote of thanks. Dr. Joshi, please.
Yeah. Thank you for giving this insightful lecture. I would like to thank, first of all, the speaker for this nice talk, Professor TC. It was very nice to hear you. You have provided valuable insights, and we could get a lot of insightful information on the basis of your talk. Next in line, I would like to thank Professor Manoranjan Sahu, who is coordinating this monthly online lecture series, who contacted you and who has been coordinating for getting the best speakers for this particular initiative of IASTA. I would also like to thank Neeraj, who is heading IASTA at this moment, Ashwini, who was present, rest of the EC members, executive committee members of IASTA, and last but not the least, I would like to thank all the participants who were present to hear Professor TC and who were ultimately part of the discussion, which was very nicely coordinated by Neeraj. Thank you, one and all, and see you in the next lecture.
Okay, bye bye, Professor House.
Bye bye. Thank
Thank
you.
you. Yeah, thank everyone. Yeah, thanks for being here and thanks for inviting me. See you next time somewhere. Thanks.
Yeah.